Good morning. My name is Tejas Budwal.
And my name is Aryan Sahu.
We will be presenting on the topic Deep Air Quality Forecasting using Hybrid Deep Learning Framework. So, firstly, what is air pollution? It arises from natural and human sources like industry, forest fires, and volcanoes, releasing harmful chemicals. This pollution leads to millions of global deaths yearly, with indoor pollution being a significant contributor. Global monitoring networks exist but have limitations due to high costs affecting accuracy. Our prediction model lacks uncertainty estimation, hampering effective control and mitigation efforts. Global air quality networks face limited coverage and high installation costs, approximating Rs 1.5 crores per station yearly in India, affecting accuracy. Existing prediction models often lack uncertainty estimation, which hampers control and mitigation efforts. We have also read different research papers and have shown the NSCEP data for the production cost, which highlights the high cost of maintenance and production of air quality monitoring systems. And so we need to devise a good machine learning model so as to mitigate this issue. Now, let us explore some innovative approaches in the field of air quality forecasting and monitoring. These advancements in previous works have the potential to significantly improve our understanding and management of air quality. Semi-supervised air quality forecasting. Zheng et al. Introduced a semi-supervised learning approach using a co-training framework with true classifiers, an artificial neural network, and a conditional random field. By combining labeled and unlabeled data, this method enhances the accuracy of air quality predictions, aiding in forecasting. PDC model for PM 2.5 temporal dependencies. Zhou et al. Proposed a probabilistic dynamic causal model that uncovers the dynamic temporal dependencies of PM 2.5 levels using Lasso-Granger analysis. This model provides insights into the factors influencing particulate matter concentrations over time, improving our ability to predict PM 2.5 fluctuations. Next, we have the hybrid model for 1 day ahead PM 2.5 forecasting. Zhou et al. Developed a hybrid model for 1 day ahead PM 2.5 forecasting. This approach combines ensemble empirical model mode decomposition with a general regression neural network. EEMD simplifies complex air quality data, and GRNN uses these components for accurate predictions, enhancing precision in PM 2.5 forecasts. Next, the real-time citywide air quality inference. His et al. Introduced a method for real-time and fine-grained air quality inference across a city. Their semi-supervised inference model utilizes available data resources, including labeled and unlabeled information, to provide detailed, up-to-date air quality assessments at various locations within a city. This method can greatly assist in urban air quality monitoring and management. Now let's delve into the heart of the research, the proposed model. Our model is composed of two key components, the one-dimensional convolutional neural network and the bidirectional long short-term memory. First, we will discuss what is one-dimensional CNN. This part of our model is designed to capture spatial patterns in the air quality data. The 1D CNN is adept at recognizing intricate patterns and features within the data, allowing us to extract valuable information related to air quality. Next is the bidirectional LSTM. The bidirectional LSTM, on the other hand, excels at understanding temporal dependencies in the data. It comprehends how past and future time steps influence the current air quality readings. By combining information from both directions, it provides a robust understanding of the time-based dynamics of air quality. Together, these two components work in harmony, leveraging spatial and temporal aspects of the data to create a powerful model that enhances our ability to forecast and monitor air quality effectively. Our model combines one-dimensional CNNs and bidirectional LSTM networks to analyze air quality data, considering both space and time. This fusion captures local trends, spatial correlations, and long-term dependencies effectively. This approach enhances air quality forecasting by considering the interplay between these factors, leading to more accurate predictions. Now let's break down the process our model follows to learn spatial temporal dependencies from multiple air quality stations. First of all, we start by applying conventional operations to each station's data. This step extracts local trends, resulting in a set of local trend features for each station. Next, we concatenate all local trend features from different stations together. This creates a single representation that captures time series data from all stations. To capture spatial and temporal dependencies among stations at a specific time, we employ a bidirectional long short-term memory on the concatenated data. Finally, we concatenate both spatial and temporal dependencies together. This results in a shared representation which serves as a fusion layer capturing all spatio-temporal dependencies across stations and time. This process allows our model to effectively capture complex spatial temporal patterns in air quality data, improving our ability to make accurate predictions. The model's understanding of temporal dependencies are further enhanced as follows. The fusion layer. Our fusion layer has already captured and shared spatial and temporal features across different time series data. Concatenation with the weight Wi and Pi. To refine this understanding, we take the fusion layer and concatenate it with Wi and Bi for each time window I, resulting concatenated features M-Pi. This combination results in a set of concatenated features M-Pi that capture the combined information for each time window. By doing this, we gain a more comprehensive understanding of the spatio-temporal dynamics within different time windows, ultimately improving the accuracy of our air quality predictions. In our model training process, our primary objective is to minimize the overall error, which we represent as Ci. This error metric reflects the accuracy of our model's predictions for training samples within each time window time series. Here are some key points to understand about our training process. The time windows. Our training data consists of multiple time window time series inputs denoted as I, ranging from 1 to n. Here n represents the total number of time windows we consider in our training process. Next, we have the input samples. Within each time window input I, we have individual input samples indexed by j, ranging from 1 to m. These samples collectively form our training data set. Our objective is to fine-tune our model to minimize the error Ci for each time window, ensuring that it accurately captures the spatio-temporal patterns in the air quality data. The training objective function is shown here. A typical CNN consists of three layers: convolutional, activating, and pooling. Multiple one-dimensional filters are applied across all time steps of air quality data. The LSTM consists of four parts, which are as follows. The input gate. It is responsible for deciding which new information to input into the memory cell. The forget gate. It determines how much of the existing information in the memory cell should be discarded. Output gate. It decides how much information should be passed to the next step or to the input. The self-recurrent part. It allows information to be looped back within the same time step like a typical RNN. Further, we show how the bidirectional LSTM conducts its forward pass. First of all, we have the input gate. Next, we have the forward gate, the output gate, and then the self-recurrence, which applies the tanh activation function. Memory gate is composed of two parts. The first pass is calculated by combining the previous internal memory state with the forget state. The second part results from element-wise multiplication of the self-recurrent state and the input gate. HT, which denotes the output for our forward pass. And then similarly, we apply the same algorithm for our backward pass. In the end, we concatenate the vector HT for the forward pass and the backward pass output HT dash. Through the above process, the BiLSTM can learn both past and future features of time series data, and the predictive output is generated from past and future contexts.
So now I will present you with the experimentation part. We will compare our proposed model DAQFF with two datasets, mainly Beijing and urban air quality datasets. Both contain features like PM2.5, CO2, SO2, dew point, etc. But we will specifically focus on PM2.5. So for the configuration part, we'll use intervals for 1 hour, time span of about we have given the timestamp. And now for the use records, we are using 43,824 for Beijing dataset and 2,78,023 points for the urban quality dataset. And in the Beijing air quality dataset, we are using only one station, and for the urban air quality, we are using 36 stations. Now, to minimize the overfooting, we use the dropout policy with edge probability of about 0.3, batch size of about 32, epoch of about 100, lookup size of about 1. We use activation functions like tanH for RNN, ReLU for CNN, ADAM optimizers. We have used various baseline models such as shallow machine learning models like SVR, which is support vector regression, and other deep learning models like RNN, CNNs, LSTMs. Now, we have used 3 convolution layers for the local trend features. We have given the configuration 64,5, 32,3 and 16,1, which are the neuron output layers with the ReLU activation. We have also used bidirectional LSTM layer with 128 hidden neurons for temporal features, and the logs function we are using is mainly mean square error, MSE. We'll now compare our model with deep learning models like RNNs, LSTM and GRU, which is basically gated recurrent units, and shallow machine learning models like SVR, support vector regression, which uses different kernels like RBF, polynomial or linear to map input to higher dimension, which could be used to learn nonlinear trends. In the first experimentation, we have compared the models for the single step forecasting, which mainly predicts output for the next hour. Now, we can see here that our proposed model DAQFF achieves much superior accuracy, like error RMSE 8.20 and maximum absolute error of about 6.2. Similarly, we can see the trend in the urban air quality datasets, which our proposed model achieves an RMSE of about 11.8 and a maximum absolute error of about 9.96. This means that our deep learning models, we can see that the deep learning models like LSTM, GRU, CNN have much less RMSE and maximum absolute error compared to the shallow machine learning models like SVR with kernel, polynomial, linear or RBF. This means that the deep learning model are more effective for air quality time series forecasting in a single step forecasting than the shallow machine learning models. Now, after evaluating different models, we also compared how error depends upon the lookup size and the epoch. In the first diagram, you can see that in the early stage of window size, RMSE get decreased, but when we increase the lookup size, the RMSE starts increasing. So we can say that at lookup size 9, RMSE at its lowest. Similarly, for the epoch, it follows the similar trend that as epoch get increased, we can see that at the early stage, the RMSE is decreasing, but as the epoch gets increased, we can say that the model is overfitting. So at about 70, we can say that about epoch 70, we can say that it achieves the lowest RMSE. Next, I will show you the comparison between SVR, LSTM and our proposed model DAQFF on PM2.5 Beijing dataset. We can see that in the highlighted area, our proposed model closely resembles to the ground truth in contrast to the shallow machine learning models like SVR. This is the similar case in case of urban air quality dataset, which also shows the similar trend that in the highlighted area we can see our proposed model closely resembles with the ground truth. Now, for the multi-step forecasting, we can see that in the table 3, our proposed model beats all the baselines, capturing RMSE of about 43.5 and a maximum absolute error of about 27.5. Similar trend is followed in urban air quality dataset. But here's the catch. The testing error of a classical DL model are larger than the shallow machine learning model in this dataset. So here's a question. Is it true that for the multi-step forecasting, SVR, specifically SVR linear, is better than the DL frameworks? Well, the answer is not quite this. For the early prediction time, we can see that specifically SVR linear has achieved a much lower RMSE than all the other DL frameworks like RNN, LSTM. But as we go to a higher time period, we can see that the prediction of DL frameworks performs better than any of the shallow machine learning models. Now, here is the comparison for the next hour, the next third hour, and the prediction for the next sixth hour between LSTM SVR linear, and our proposed model DAQFF. As we can see, as the time moves forward, deep learning frameworks like LSTM and our proposed model tends to perform much better. In the same trend, we can see that in the urban air quality dataset, where in the early time prediction, like from the first to sixth hour, SVR linear is performing better. But as the prediction time progresses, deep learning frameworks performs much better and achieve much less RMSE as well as maximum absolute error. Now, this is a comparison between three models on urban air quality dataset based on 36 stations. We can see that our proposed model closely resembles to the ground truth. Then the LSTM works comparatively good. Then we can see that SVR linear performs the worst out of three. Now we will compare our proposed model with the state-of-the-art model proposed by the researcher Zeng. He also used urban air quality dataset for evaluation. In instance, where the prediction time is less than 6 timestamps, we can see that our proposed model DAQFF is much less favorable. But this can we say that our proposed model is bad? No, we can't say that. We can see that as the time progresses, we can see our model achieves much superior performance in comparison to the model proposed by Zeng. So, this concludes our summarization on the research project. Thank you.
Thank you.